Hello. In this video, we are going to discuss the synthesis of amines, particularly the synthesis of primary aliphatic amines, and then in the second part of the video, we are going to discuss exhaustive methylation. Recall that a primary amine has the general structure RNH2, where we can think of one of the hydrogens of ammonia conceptually as having been replaced by some alkyl group. We recall that ammonia, being a base, can act as a nucleophile, and that if we have a haloalkane, halogens, particularly chlorine, bromine, and iodine, make excellent leaving groups. Therefore, particularly if this is a methyl or primary haloalkane, then we can employ the SN2, the nucleophilic substitution second order reaction, as a way of synthesizing a primary aliphatic amine. We know that the halogens, being very electronegative, polarize the carbon to which they are attached and make the carbon electron deficient, partially with a positive charge. Therefore, the carbon directly attached to the halogen is an excellent site for nucleophilic attack, a reagent that comes in that has a lone pair available for sharing. So the lone pair on the ammonia will attack the electron deficient carbon, while at the same time, simultaneously in the transition state, the carbon halogen bond will break, with the electrons going with the halogen to form a halide ion. The result of the substitution gives us a protonated primary amine and the halide ion, which was the leaving group. In the next step, the protonated amine can react with a base that would either be the solvent or excess ammonia to abstract the proton from the protonated amine. After abstraction of the proton from the protonated amine, we are left with our main organic product, which is the primary amine here. The proton leaves with a base, and we are left with the halide ion, which is the leaving group on the substrate from the SN2 nucleophilic substitution attack. In the first part of the video, we are going to look in detail at the synthesis of four specific amines. In the first case, we are going to have the nucleophilic attack of ammonia on chloromethane, or methyl chloride. Immediately we know that this must be proceeding by an SN2 reaction, because we know that the likelihood of formation of a carbocation from a methyl substrate is very, very, very low. So therefore this must be proceeding by an SN2 reaction, and we know that we have nucleophilic attack on the electron deficient carbon there, and then we have bond breaking, the electrons leaving with chlorine as chloride. We recall that once the chlorine has left as chloride, we are left with an intermediate, which is a protonated amine, which almost immediately loses the proton to solvent to form our organic product, our major organic product here, which is methylamine. Since we've already shown the mechanism in detail, we are going to concentrate now simply on the major organic product, which in this case is methylamine. Please see the following figures to show computed structures for reactants and products for the synthesis of this compound by nucleophilic substitution in both the cases where we have chloromethane and bromoethane. In both cases, we end up with exactly the same product, and we'll see in a table near the end of the video that when we compare the energies of activation, that as we expect, the energy of activation is lower in the case of bromomethane because bromine is a better leaving group than chlorine is. In our second set of reactions, we are going to have nucleophilic attack of ammonia on bromoethane. Again, the presence of the halide directly attached to carbon makes this carbon directly attached to it electron deficient. So we have nucleophilic attack by our nucleophile on this particular carbon here, and in the process, we get our major organic product, is the compound ethylamine. Please see the following figures for computed structures for the reactants and products and transition state for the reaction with either bromoethane or chloroethane. In both cases, we get the exact same product, which is ethylamine. Next, we react ammonia with 1-chloropropane, or 1-propyl-chloride, if you want to call it that way. Again, here we have a primary haloalkane, which makes it quite suitable for SN2 reaction and unfavorable for an SN1 type reaction. This carbon is attached to the chlorine, so it's electron deficient, and we end up with a nucleophilic attack. On this particular carbon, we have bond breaking, and the chlorine leaves as chloride, and we are left with our major organic product, which is 1-propylamine, or N-propylamine. So in each of the cases so far, we've been adding slightly longer alkyl chain in place of one of the hydrogens to make a primary amine. Please see the following computed structures for the reactants, products, and transition states for the reaction of ammonia with either 1-chloropropane or 1-bromopropane. Again, in each case, we end up with an identical product, which is going to be the 1-propylamine. I have not generated the structures, but we could also have run the reaction with iodine as our leaving group. So we could have used the 1-iodo-propane. And we recall, as we know from other information, that just as bromine is a better leaving group than chlorine is, iodine is an even better leaving group than bromine is. In general, the reason why we might want to use one substrate with a particular leaving group instead of another one is very often based on cost. So in many of the examples you'll see chlorine used as the leaving group because in general, in most cases, the substrates, the chlorinated compounds are generally less expensive than the brominated ones, which are less expensive than the iodated ones, even though iodine will be a better leaving group, which means it will leave faster, so we generate our product more quickly with the iodated compounds than from the brominated ones than from the chlorinated ones. So it's a trade-off between speed of reaction and cost. In the fourth and final reaction of the first part of this video, we are going to look at the reaction of ammonia now with 1-bromobutane or 1-butyl bromide. Again, here we have a primary haloalkane, so it's going to be a suitable substrate for an SN2 reaction. So we have nucleophilic attack by the nucleophile on the carbon directly connected to the bromine because it's electron deficient. We have heterolytic bond cleavage between the carbon and bromine, so bromine leaves as bromide, and we are left with the major organic product, one-butylamine, or N-butylamine. The N in those in that nomenclature means normal, which is a linear, perfectly linear chain. So please see the following computed structures for the reactants and products and transition states for the reactions with either 1-bromobutane or 1-chlorobutane. In both cases, we get exactly the same product, the 1-butylamine, also called N-butylamine. Recall at the very beginning of this video, the very first reaction that we looked at was the reaction of ammonia on chloromethane, and we saw that the product we were going to get from that was methylamine. Now, an important consequence of this type of reaction is that our product, methylamine, is a nitrogen compound where nitrogen still has a lone pair. In addition, the presence of the alkyl group in the amine actually makes this a stronger base. Methylamine is a stronger base than ammonia is. And because it is a stronger base, it is also a stronger nucleophile. So not only is our reactant a nucleophile, our product is a nucleophile. So, once methylamine as a product forms, so long as there's still excess chloromethane present in the reaction vessel, then we have a competition between the ammonia that we started with and one of the intermediate products, which is methylamine. And we know that since this is a stronger base, a better nucleophile, it is going to react with the same substrate, chloromethane, more quickly than ammonia is. So in the competition between these two, even though there's only a small amount of methylamine, pound for pound, molecule for molecule, this is a better nucleophile, so it will react more quickly with the chloromethane than ammonia does. What will be the result of that? The result is methylamine can react with chloromethane effectively to replace one of the remaining hydrogens. So now we have a second hydrogen of ammonia replaced with a methyl group. So now we have another product, dimethylamine. So this is one of the interesting challenges in the synthesis of amines, is that if we start with ammonia, one of the intermediate products, methylamine, is actually even better nucleophile than ammonia is. So it's going to react with the chloromethane substrate to form dimethylamine. But if methylamine is a stronger base than ammonia and therefore a better nucleophile, what about having dimethylamine? Well, dimethylamine is a stronger base than methylamine is, so it's going to be a better nucleophile. So with excess chloromethane, dimethylamine will begin a nucleophilic attack on chloromethane to replace the remaining hydrogen atom. As a result, we've replaced the final of the hydrogen atoms that was originally present in ammonia with a methyl group, and now we have trimethylamine. So if we begin the reaction with ammonia and chloromethane, so long as we have an excess of chloromethane, not only do we form methylamine, we get dimethylamine, and we even get trimethylamine. Now, one further step that is a little tricky to explain is as follows. Now, we've seen in a previous video that, contrary to what we'd expect, trimethylamine is not a stronger base than dimethylamine. And we saw that that's not what we got from the electronic structure calculations, but we know in aqueous solution that that is true. But even though this is not as strong a base as dimethylamine because of steric and solvent factors, the presence of the additional alkyl group does make it a better nucleophile than dimethylamine, which is a stronger nucleophile than methylamine, which is a stronger nucleophile than ammonia is. So therefore, so long as there's more chloromethane present, trimethylamine will react with the chloromethane even more quickly than any of the other ammonia derivatives that have already formed or were the initial reactants. As a result, we can end up forming this particularly substituted ammonium ion, where instead of NH4+, we have each of the hydrogen atoms replaced by a methyl group. So this is a tetramethylammonium ion. These types, so this is ammonia. Recall that this is a primary amine because one of the hydrogens were replaced by an alkyl group. This is a secondary amine because we replaced two of the hydrogens with an alkyl group. Here is a tertiary amine. So therefore, if we replace, four alkyl groups attached to the nitrogen, we call these quaternary amines. They're also known by the short name of quats, where quat is short for quaternary. These types of compounds, particularly with longer alkyl chains, are very effective bactericidal and antiseptic compounds. So they actually have industrial applications for disinfectants. But so here is the ultimate problem is, if we want to simply synthesize methylamine, we have the danger of side reactions with the substrate to generate the dimethylamine, trimethylamine, and even up to the quaternary ammonium compound. What makes this worse is, as we add each methyl group, the resulting product is even more likely to react with the substrate than the initial ammonia was. So here is a case where if we absolutely want to generate methylamine and only methylamine, the secret to do that is to use the minimal amount of chloromethane and use a huge excess of ammonia, so that of any of the amines that are going to react with the chloromethane, it's most likely to be ammonia. If, on the other hand, we use a very small amount of ammonia to begin with and a very large excess of chloromethane, we are likely to generate particularly the trimethylamine and the quaternary ammonium compounds because of this process of so-called exhaustive methylation. So please see the following structures for the reactants and the transition states for the reactions of all these particular steps. And finally, see a table which shows the energies of activation for the transition states for each of the reactions, which shows as we start with ammonia and then go to methyl and all the way down, that the energies of activation become smaller and smaller, which means that methylamine will react more quickly with the substrate than ammonia does. Dimethylamine will react even more quickly, and so on. I thank you again for your attention. Please like and subscribe. And as always, have a good one.